again, okay. Daniel, thanks for agreeing to talk to the Harrisburg Area Geologic Society. And we have 45 participants. Looks like most of them are professional geologists in Pennsylvania. As a way of introduction to the members and attendees here, Daniel Hummer is an assistant professor at Southern Illinois University. He has a Bachelor of Science in Chemistry at Iowa State and simultaneous Bachelor of Science in Geology from there. And he has numerous publications and citations on minerals, chemistry, petrology, and of various metals and oxides, carbon and phase stability, our favorites, reactions, and even fractals. Daniel is originally from Iowa, where he received his bachelor's degree at Iowa State. He also minored in physics, mathematics, and Spanish. He got his PhD in Penn State, and I hope he enjoyed his time in Penn State. Beautiful spot. His thesis was titled Mechanisms of Aqueous Crystallization and Phase Transformation in Titanium Oxide Minerals. I'm sure most of you got the chills when you heard about the phases. After graduating, he went on to numerous high-profile postdoctoral programs. He was first working with Dr. Robert Hazen in the world-class facilities of the Carnegie Institution for Science in Washington, D.C. Finishing that, he traveled cross-country with a broken foot to continue his work in the University of California in Los Angeles. And then he returned to the Carnegie Institution in Washington as part of an international effort to apply big data analyses to questions of earth science, some of which is the talk here today. Since 2016, he's been an assistant professor at Southern Illinois University in Carbondale, Illinois. Other notable works include that he's a museum exhibit designer. He's a leading team. He leads a team of AMNH. I'm sure the M stands for mineralogy, personnel, and other contractors to design a mineral evolution exhibit for the American Museum of Natural History in New York City, which is now on display. He's the principal investigator for the Carbon Mineral Challenge, which is a worldwide effort with mineralogists and collectors to discover new carbon-bearing minerals. And if you saw Amy's wonderful introduction on our email, he and his colleagues has predicted the existence of about 146 undiscovered carbon-bearing minerals. That's where his chemistry comes in, I'm sure. He is the principal in, I covered this, the carbon-bearing minerals. He's also the associate editor for the Journal of American Mineralogists. I appreciate his time here. I love the fact that we can get him on this Zoom platform so he doesn't have to drive to Pennsylvania. And Daniel, thanks for coming, and we're looking forward to your talk.
Well, thanks very much. Can everybody hear me? Is video and audio okay?
All very
It's
good.
Great.
Okay,
Great.
Excellent. Well, thank you, Kent, for that introduction. I feel like it was better than I deserve. I've worked on a ton of different things, but one of the most fun things that I've done is help to develop this museum exhibit. So I'll touch on that a little bit. And by the way, how did you know about the broken foot?
Oh,
Why didn't
I
I
told
see
him that story.
Oh, you okay. So for those who don't know, Mike Meyer and I were colleagues at Carnegie. He was working there at the same time that I was doing one of my postdocs there with Bob Hazen, who is really one of the kingpins and one of the leaders in this new emerging field of using big data in order to explore the Earth. So thanks very much for having me. It's always really fun to do these talks. And by the way, as we go along, if anyone has any questions, please feel free to just jump in, just unmute yourself, raise your hand or whatever, and let me know. And you're welcome to ask questions as we move through the talk here. So I am going to try to share my screen right now. Let's see if that works. I'm going to turn on my slideshow here. Here we are. And let's see if I'm able to share that.
I see it.
Okay, does everybody see the title slide there?
We're good.
Okay, excellent. We'll get started. I'm sorry, by the way, that it took me a few minutes. I was trying to join the meeting through Firefox, and it tried it over and over again, and it wasn't working. And then I tried it with Google Chrome, and it worked. So how about that? I guess Google makes some pretty good things. So as I said, thanks everybody for joining me. What I'm going to present today is really about data mining the past. It's about using really big data sets of mineral occurrences and sort of statistically analyzing them and looking for trends and learning as much as we can about both Earth's present and Earth's history by looking at these large data sets. And I've been doing, as Kent mentioned, I've been doing this for several years now with the help of a lot of different collaborators, people at all of the institutions that you see represented down here at the bottom of the screen. And before I go into the material, actually, I just want to give lip service to some of these collaborators.
Dan, real quick.
Oh, yes.
Sorry, it wasn't weird for me because I've been doing this on Zoom myself so much. But you're sharing the other part. You're sharing the instructor screen, not the
Oh,
slide.
am I? Oh,
Yeah.
interesting. Okay.
I can see your mouse move.
Okay, let me see if I can you see the next slide?
Yeah, I can see them.
thing?
Yep.
Yeah, okay. All right. That means let's see. There we go. Is that better?
Yep. Good to go.
And
Keep
now
going.
it's just the full slide. Okay. Great. I found the button to switch those. So that's good. Thanks for letting me know, Mike. Okay, so I just wanted to pay lip service here to some of the collaborators that I've been working with who have just been amazing. It's been an amazing experience working with all of them. One of the primary ones is the one all the way over on the right side there, Robert Hazen at the Carnegie Institution, but also many other people, Andrew Knoll, Dimitris Virginsky, Paul Falkowski, who is at Rutgers University, Bob Downs at University of Arizona, and Peter Fox at RPI, who very sadly passed away just a matter of months ago. And that was a tremendous loss to our whole community of people who are working on this big data. So I just wanted to mention some of those people who have really played an instrumental role in developing these databases and the ways that we're analyzing the data in order to learn more about Earth's history. So now let me jump into the material here. So first of all, let's review just for a moment what a mineral species is. So when we're trying to find mineral species and count them up, learn about how many of them there are, what is it actually that we're counting? Well, a mineral species is actually a unique combination of a particular chemical formula, so a particular chemistry, and a crystal structure. Okay, so things with the same chemistry but different crystal structures are still a different mineral species because we have those two simultaneous components. Right now, we know about somewhat over 5,500 mineral species that have been discovered so far on Earth. A few of the more lovely ones are pictured right here, but of course they come in all different chemistry, all different sizes, shapes, and colors, and it creates a really beautiful kingdom of things for us to study. Okay, now where does all this data come from that we're using to do these studies? Well, an awful lot of it is actually put together at the University of Arizona in what's known as the RUFF project. And you see that up at the top of your screen there, rruff.info/IMA is the website you can go to. And by the way, this is open source. Everybody can go and look at this listing of minerals and look up more information about any mineral species you want. You can see there's over 5,000 species are listed alphabetically right here in this left-hand part of the screen. And then down at the bottom, you can see a periodic table. So you're able to click on particular elements and search for minerals that involve those elements. And then notice up towards the upper corner there's several other buttons that you can go to find more information about any particular mineral that you've clicked on. And in particular, for our purposes, we have a button there that says evolution. And that evolution database, button contains a database of many different geologic ages that are associated with that mineral. So in other words, not only do we know that the one that it's pointing there to, Albrechtschroffite, not only can we find basic information about that mineral, but we can look at all the geologic ages that are from the literature of when that mineral formed at different places in Earth's history. Okay, so we can do a lot of different things with all of this mineral data. One of the things that we've been trying to do is basically study minerals ecology. And this was a term that was actually coined by Bob Hazen many years ago. And the way that we define it is just simply studying the diversity and distribution of minerals all over the world, all their occurrences all over the world, in all of the various chemical, physical, and biological environments that they occur in. Okay, so that's mineral ecology. So very akin in a way to biological ecology, but instead we're just talking about non-living things and where they occur rather than living things. Okay, now when we look at how many of the different minerals there are all around the world, what we find is something really shocking. When we look at that distribution, it turns out that the distribution of these 5,500 or so minerals conforms to exactly the same statistical distribution as words in a book. Now that's kind of mind-blowing in a way. Why would the distribution of minerals have anything to do with language and linguistics? Well, they're tied together by this common mathematical phenomenon. So to illustrate that, think about, what does this have to do with books? Think about picking up any book. So for example, in the image here is an old copy of Christmas Carol by Charles Dickens. And imagine that you opened up this manuscript of A Christmas Carol and you pointed to a random word and looked to see what word that is. Well, there's a few words that you would find really commonly, okay, that you're fairly likely to find on that page in the book, okay, like a, and, the, is, okay, all of those words are super, super common. But if you think about it word by word, most words are rare. Okay, the word candlestick is probably not going to appear in that manuscript very often. The word onomatopoeia is probably not going to appear very often. And that's the vast majority of the words in the English language. Most of the words in the English language are rare. Okay, it's only a few words that are very common that we use often, and then the distribution dramatically trails off after that. Okay, but these rare words are still important, because those rare words define the diversity of language that you find in this manuscript. And the pattern of rare words that you find can actually be used to figure out who the author is. And linguists do this. They analyze the occurrence of words, and you can actually figure out who authored an unsigned manuscript by looking at those word distributions. And not only can you do that, but you can also extrapolate and learn what the author's total vocabulary was. And that's, remember, all because words conform to this particular type of distribution. So, as it turns out, minerals on Earth behave in exactly the same way. Okay, the distribution of these 5,500 mineral species conforms to this same distribution. And therefore we get a few minerals that are really, really common that make up most of the Earth's crust. Okay, things like quartz, calcite, feldspar. Okay, I'm sure everybody has heard of these minerals because they're so extremely common. But most mineral species are rare. Abelsenite and bobdownsite, who's actually named after one of our collaborators, all of those mineral species, okay, most of those 5,500 mineral species are actually very rare. They're only found in a few places on Earth. And so all of those rare minerals follows this distribution that we call a large number of rare events frequency distribution. Okay, and just like we can figure out authorship and we can figure out the total vocabulary of an author, we can also look at Earth and look at this and compare it to this distribution and figure out what the total mineral diversity is and how many minerals are missing that we don't know about yet. So it enables some really incredible predictions once we start using these data sets and looking at their patterns. So let me show you on the next slide how that works. Okay, so on this graph, if you look at the y-axis, we have the number of minerals found at a particular number of localities. Okay, and then across the horizontal axis, I have the actual number of localities. So I'll use my cursor here to point. So at a number of localities equal to 1, so 1 locality, I have over 1,000 mineral species. That means that 1,000 out of those 5,500 mineral species only occur at exactly 1 place on Earth. There are about 600 mineral species that occur at only 2 locations on Earth, and so on and so forth. And as I increase the number of locations, the number of minerals that are found at that many locations dramatically dives downward until the number that are found at many, many locations is actually a fairly small number of mineral species. Okay, so that's exactly what we mean by most minerals are rare, only a few of them are common. Okay, and this was published by our collaborator several years ago, our collaborator Greta Heisted, who's now at Purdue University. Okay, so like I said, this distribution in which most species are rare, but a few are common is called the large number of rare events distribution. Okay, another way to visualize this distribution, and this is really the way that enables us to predict how many minerals there are, is to instead graph it in a somewhat different way. Okay, so on this graph, I'm going to use number of observations or just number of mineral counts, number of observations of one particular mineral at one locality is on the x-axis here, okay? And you can see it gets to really large numbers really quickly. On the y-axis, I'm plotting not the number of mineral counts that I've done, but the actual number of different unique mineral species that I have. Okay, so the number of approved mineral species that we know are different from all the other mineral species is on that axis. So as I begin counting, I'm just going to go to a particular location on Earth. I'm going to look at that location and say, okay, I see quartz at this location. Okay, well, at my very first observation, my very first tick on the x-axis, I'm going to say, okay, well, that's new. I haven't seen quartz before because I just started. Okay, so there's one tick on my x-axis and one tick on my y-axis. And as I keep going to different places and finding minerals, I say, okay, I have orthoclase at this location. Okay, that's another tick upwards. But as I go to different locations and look at the minerals there, and so I increase those mineral counts along the x-axis, initially I discover new minerals really rapidly, because most of what I'm seeing, I haven't seen before, because I haven't been at it for very long. But as we continue, it starts to taper off. The new discoveries start to taper off because most minerals we have seen before. Okay, so here's where we were actually as of February of 2014. But 2014, for example, we had about 4,800 mineral species. Okay, so we were at about this place on the graph. Well, as we continue looking in different places, we're likely to find more minerals, but more slowly. Okay, the y-axis is going to increase more slowly. So if I extrapolate into the future, it turns out we don't have to look every place on Earth, we can statistically extrapolate into the future and see that we would expect about 6,400 total mineral species that exist on the Earth right now. But of course, we haven't found all of them yet, okay, because we would need to project into the future in order to find all of them. So based on that, we can make the prediction that there are over 1,500 mineral species at least that are yet to be discovered and have yet to be described using standard techniques. Now, of course, if in the future, all of a sudden we develop new technology for finding minerals, well, then that could change. That changes the pace of discovery. And so therefore that changes the extrapolated value of the number of minerals that we would expect. Okay, so for example, we can play this game with not just with all minerals, but with certain subsets of minerals that have particular elements such as carbon. So we wanted to do this because, of course, carbon is a really crucial element up here on Earth's surface. It's a very common element. There are lots of minerals that contain carbon. And obviously, another important thing about carbon is that life is based on carbon. Okay, all of life uses carbon-based molecules in order to function. So understanding the diversity of carbon chemistry and carbon minerals on Earth also helps us to understand life and the role that it played on Earth. So we looked at carbon minerals. Here's that same sort of graph that I showed you initially, where we have the number of localities here on the x-axis. And this is probability, but it's really the same thing. It's really just the relative number of minerals here on the y-axis. And when we look at different carbon minerals, we see, so calcite is known from 25,000 different localities, okay? So it's way far over, it's not even on the screen. It's way far over to the right on the x-axis. So it's one of the very few common mineral species. But as I work my way left on this graph, I'm going to get to more and more rare carbon mineral species. So for example, diamond is known from 700 different locations. Okay, so that's starting to get a little bit rare, but ironic, isn't it? We think of diamond as this, you know, this very rare, precious gemstone. In reality, in the grand scheme of things, it's actually pretty common. Okay, at 700 locations is a hefty number of locations. So diamond isn't really that rare. Something like Bob Downsite that I mentioned is named after one of our collaborators. He runs the database at University of Arizona, is known from only 3 locations on Earth. And my former supervisor has one named after him called hazenite. It's actually a waste product. It's actually bacterial poop, as a matter of fact. And it's only known from 1 location on Earth. Okay, so we can get to progressively more and more rare carbon minerals. And indeed, you can see it conforms to exactly this same distribution, where many minerals are rare and only a select few minerals are known from many, many localities. Okay, so where are all of these missing carbon minerals? Okay, they seem important to know about. It tells us about the carbon chemistry on Earth. We know now approximately how many there should be. We can use those techniques to develop this, but how do we find them? So Bob Hazen and I talked, and we developed this thing called the Carbon Mineral Challenge. It ran from 2015 to 2019. So about 4.5 years or so, we were trying to do this. It was open to everybody, all amateur and professional mineral collectors, professional mineralogists, and so forth. It was sponsored by an organization called the Deep Carbon Observatory that we were working with at the time. And so we basically sent the word out, to professionals and amateurs alike, mineral societies all over the world, and said, look at your specimens, look out for these things, look for things that are new that could potentially be carbon-bearing minerals. And we ran this challenge, and by the end of the challenge, we actually found quite a few of these predicted new minerals. So in particular, here's the graph for just the carbon-bearing minerals. If we look at the accumulation of unique species, okay, so the graph that continues going up. And when you look at that graph, here's the number of mineral counts, and here's the number of known different carbon mineral species in particular. And at the time that we initiated the challenge, turns out there were 406 of them. But when you extrapolate it into the future, the statistics told us that there should be about 551. So in other words, that gap, that missing gap, told us that there were about 145 carbon minerals that were undiscovered. that we needed to find somewhere out there in the natural world. So we went about trying to find them. Now, using the statistics, we know how many there should be, okay? And that's that number down at the bottom of your screen, 145 new carbon minerals that we need to find. But what are they? Okay, well, for that, we need to use different techniques. We need to go to something just beyond the statistics. We need to look at the patterns of what other elements occur in these carbon minerals. Okay, what compositions would we expect? What kinds of environments would we expect them to be in? So we wrote an entire paper, actually, and we used a couple of different strategies to predict what these missing carbon minerals were. So one strategy is to simply take carbon minerals that we already know about and change their chemistry just a little bit, okay? Substitute one of the elements in that mineral with a different element, okay? Maybe a chemical element that behaves in a very similar fashion, and predict that, you know, maybe that mineral exists as well. So for example, at the beginning of the challenge, we knew about this carbonate mineral, parasite cerium. Okay, and parasite cerium has this chemical formula that you see right there. It's a calcium cerium carbonate. Okay, well, cerium is a rare earth metal, and all of the rare earth metals, okay, especially the ones towards the beginning of the series, are all very, very similar chemically. They behave in a very, very similar fashion. So if we have a mineral with calcium and cerium, it stands to reason that we probably could also have a mineral where we just substitute the cerium with lanthanum. So that's all we did. We substituted the cerium with lanthanum, and we said, well, maybe parasite with lanthanum exists. So we predicted that as one of the carbon minerals to look for. Now, it turns out during the course of the challenge, the very first mineral that was found during the time period of the challenge was parasite lanthanum. It was found by somebody. One of the people taking part in the challenge found parasite lanthanum, and there it is. It's those orangish crystals that you see embedded in the matrix right there. So that was the very first mineral that we found, and it was one that we had specifically predicted should exist. So that was a really exciting start to the challenge. The second strategy that we used was to look at synthetic compounds, okay, materials that we already know from the lab that could potentially form in nature. So we looked for natural analogs, natural occurrences of these synthetic compounds. So for example, calcium carbide has carbon in it, and it's a chemical that is widely used in labs. It's used to perform reduction reactions and things like that. Okay, well, but we've never found it in nature before, so it's not technically a mineral species. Can we find it in nature? Well, maybe in a reducing environment, or maybe in an environment where a really intense discharge of energy has happened in calcium carbonate. So for example, lightning strikes some limestone. Well, maybe that forms a new calcium carbide mineral that is the same as the synthetic material that we know of. We could call it carbidite. Now, as it turns out, during the course of the carbon mineral challenge, we did not find this thing that I called carbidite. We didn't find any examples of that. So that one is still missing, could still be out there somewhere. But during that 4.5 years, we actually, as a community, discovered 31 new carbon-bearing mineral species. Okay, that's pretty good considering 140 or so is what we were looking for. That's a significant chunk of them. And we found them in 4.5 years just by saying, hey, let's actually go out and look for these things rather than just finding them by happenstance. So here on your screen, I'm plotting just the number of different mineral species. Okay, so the fraction of carbon mineral species that were discovered in each of these different years. And you can see that it bounces around quite a bit. Okay, we started the Carbon Mineral Challenge in later 2015, and it ran sort of through the beginning of 2019. So here's all the years of the challenge that are highlighted in red right there. And if you compare the frequency with which we were discovering carbon minerals before that, okay, so in other words, there's the 8 years or so before that, the percentage of newly discovered minerals that had carbon in them was averaging about 3.6%. During the years of the Carbon Mineral Challenge, new mineral discoveries contained carbon about 5% of the time, okay? And there's the margins of errors that are shown right there. And I did a statistical test. Now, of course, this is still a little bit iffy, but I did a statistical test to see, is that actually a statistically significant difference? And the answer was barely. It was barely a statistical significantly different data set. At a p level of 0.025. Okay, so you normally say below 0.05 is the level of significance. So new carbon minerals at an accelerated pace. Okay, so we've gone over in this first part of the talk, we've gone over some things about how we learn about the way that minerals are distributed on Earth right now. And we've learned about how we can find how many minerals there are total and how many minerals are out there that we might be missing. Now, in the second half of the talk, I'm going to focus on the evolution of minerals. Okay, so in other words, the development of mineralogy through space and time, okay, throughout all of Earth's history. Okay, that's more or less the way that we define mineral evolution. Now, I feel like the word evolution has a lot of different connotations to it. So I want to define specifically what we're talking about. What do we mean by mineral evolution? Okay, so for example, what we're talking about is a change that takes place over time in, number one, the diversity of mineral species, okay, in terms of the total number of different mineral species that we have on Earth at any given time. But not only that, also the relative abundances of minerals. Okay, at some point in Earth's history, some minerals were more abundant than other minerals, and that can shift over time. We're also talking about the compositional ranges in minerals. Okay, maybe calcite used to have a lot of strontium in it, for example, but maybe as time went on, the strontium got dispersed, okay, and the composition of calcite changed over time. And we're also talking about the modes of occurrence and the different grain sizes and shapes of minerals and the way that they appear in the Earth. Okay, that also has changed over Earth's history, undoubtedly. So all of those things are folded into mineral evolution. Let's also talk about that word evolution here for a moment. The word evolution can have a few different meanings. Okay, so one of the meanings, the broad meaning, is just a change over time in something. Okay, something changes over time. So that encompasses a lot of things because a lot of things change over time. But in the context of minerals, we can mean it, for example, in the work that Norman Bowen did about a century ago, trying to figure out the order, the specific order in which minerals would crystallize from a magma. And of course, when he did his work, what he learned is that at high temperature, we start out crystallizing minerals like olivine, and then we get pyroxene, and then we get hornblende, and it proceeds through, the minerals are added in this very particular order. So that could be an example of mineral evolution. The rock evolves over time in the sense that it crystallizes new minerals at very specific times and in a very specific order. Okay, there's also, when we talk about evolution, there's also an implication that things are becoming more complex over time. We have a complexification process over time because there's more and more mineral species. They're occurring in more ways. Okay, one mineral can transform into another. And so the situation is becoming more and more complex as we move through its history. Also, evolution is meant to imply, in some cases, a hereditary process. So in other words, this is what we get with living things. One living thing has a particular genetic makeup that gives it particular traits. Okay, it reproduces and it passes many of those same traits on to its offspring, which then themselves reproduce and pass on those traits to their offspring. And we get a slow shift and diversification in traits over time. Okay, so that hereditary process, as we know, is what governs biological life. Okay, but, and I want to be very clear because I know I'm using the word evolution here, and that's a word that's already used by the biologists. We are not talking about minerals reproducing and a mineral crystal changes over time into some different thing like you see on the image here. Okay, so that would be Darwinian biological evolution. That's not the process that we're talking about here. We're not talking about a single mineral, changing over time and changing into something else. Instead, what we're talking about is the complexification over time, the formation of these new mineral species through a whole combination of different chemical, physical, and biological processes. That's what we mean by mineral evolution. Okay, so what have we learned about mineral evolution, looking at all this mineral data? So I'll get into that now. Well, one of the exciting things that we've learned is that there are certain periods in Earth's history where Earth's mineral diversity seems to jump up, okay, where new mineral species seem to be formed at a more rapid pace than at other times in Earth's history. And we've actually known about this for a long time. If we look, for example, at data from the mineral zircon. Okay, so here are some lovely zircon grains, and geologists have been looking for these for a long time. I'm sure some of you probably know geochronologists. Okay, this is what geochronologists do. Geochronology is largely the study of zircon. You look for these zircon grains and you use a tool like uranium lead dating, and you figure out how old they are, and you look at when all of these different zircon grains formed across Earth's history. Okay, and when you plot up a histogram of all of these ages of zircon grains through Earth's history, you get something that looks like this. So there's an exciting trend here where, so this is 3.5 billion years ago, all the way here on the left of this graph, and then the present day is all the way on the right of this graph. And what you see is that a lot of zircons formed in these pulses during times where supercontinents were being assembled. Okay, so during Kennerland, during Columbia, during Rodinia, Panotia, and then again during Pangaea, all of them contain spikes in the formation of zircon. Okay, so there was extra mineral formation going on during the cycles in which these supercontinents were forming. Okay, we can also see the same sorts of trends in subsets of minerals, entire groups of minerals rather than just one particular mineral species. So for example, in the evolution of mercury minerals, mercury minerals formed through time, and you can see some of this in this graph here. There were pulses of mercury mineral formation that also occurred during exactly these same time intervals. So for example, during the formation of Kennerland. And we can statistically see that indeed that is the case. It mirrors many of the periods in which zircons were being formed. So, and in fact, there they are, shown in the green lines there. Those are some of the common periods in which we see increased mercury mineralization. Okay, so there's something about the formation of supercontinents and the tectonics that are going on, the various different processes that are moving plates together that creates new pressure and temperature environments in order to produce new mineral formations. Okay. So armed with all of this knowledge and the knowledge that we have so far about mineral evolution, I was asked by the American Museum of Natural History to help in creating an exhibit that would show the public how minerals have evolved over time and kind of summarize the important stages. So this is a little bit of a grainy photo because I haven't actually been there yet because of the pandemic. Sadly, I haven't been able to see the completed exhibit in person, but at one point I did travel to New York and I did help them with the design. And we picked out particular minerals and I outlined different stages in Earth's mineral evolution to show. And here is a photograph of it. This is a family friend of ours. This is their daughter that is standing in front of the exhibit that I helped design. And you can see here that there is this spiral timeline. It starts in the very center here with the Big Bang, and then it spirals outward, and it delineates different stages of Earth's history and the different mineral evolution that took place in each stage. So if we were to zoom in there and take a look at those stages that I show in the exhibit, this is what we would see. Okay, I basically split mineral evolution into 7 basic stages of Earth's history, or really the history of the entire universe. So you can see here the kind of stage 0 is the Big Bang, and then the early universe is stage 1, the birth of the solar system is stage 2, and so on and so forth. And I split it into 7 different stages that you can see numbered there. The young Earth, where geologic processes really got going, on the initially formed Earth and the early oceans, we sort of threw together, but we split them into 3A and 3B because we think they were happening at about the same time, but it was different processes that we're talking about. Okay, so we've got 0, 1, 2, 3A, 3B, and then 4, 5, 6, 7. Okay, and I'll just kind of briefly summarize these different stages. So for example, in stage 1, one of the first minerals that formed was actually in the atmospheres of stars as the first light elements besides hydrogen and helium were getting going. First, we got hydrogen, helium, and then lithium, beryllium, boron, and element 6, which is carbon. And carbon was one of the most common elements to form in the outer portions of stars. So in the atmospheres of those stars, we believe that one of the first minerals to form was diamond. So that's why I've put a little diamond right there. So diamonds formed early on in the universe. When our solar system formed, okay, materials started aggregating together and cooling down for the first time. And that formed some of the first grains of olivine. So that's what's shown right there for stage 2. In the young Earth, okay, once the Earth formed and began cooling down, it formed a basaltic crust that then differentiated into different compositions like mafic and felsic compositions. So we got the first quartz and feldspar during stage 3A. And then the oceans, shortly after that, the oceans formed, and all of that water chemically altered minerals. And we formed things like some of the first clay minerals. Okay, so clay minerals pop up right there. This stage 4, the Earth's dynamic crust, is delineated by the initiation of plate tectonics. So many of the geologic processes that we're familiar with today that generate mountains, volcanoes, earthquakes, okay, that got different pieces of material, different crustal plates moving in different ways. It released fluids, okay, hydrothermal minerals like pyrite formed. So many of those minerals formed during stage 4. Then something really, really crucial happens. Okay, now up until stage 4, at the end of stage 4, we had about 1,500 mineral species. So all of those geologic processes that took place in stages 0 through 4 got us to 1,500. But I told you earlier in the talk that there are actually now over 5,500, and we're actually counting towards 6,000 now, total mineral species. Okay, so there's the majority of them left to go. So what was the crucial thing that really exploded mineral diversity? Okay, because right now, all of these chemical and physical processes resulted in the 1,500 mineral species that we got up through stage 4. Okay, how did we get to the 5,500 that are on Earth today? The one ingredient that we needed, as it turns out, was life. We needed life in order to get the rest of our mineral diversity. So how could that be? But living things are based on totally different materials, right? So why would life be such a crucial ingredient in what's happening in the solid Earth? Okay, well, life completely changed the planet. Okay, in stage 5 here, life emerged and it fundamentally changed the chemical environment that was experienced by everything on the surface of the Earth. Okay, so let's take a look in detail at how that happened. So we think that the origin of life was right around 4 billion years ago or so. Okay, we have good evidence for life going up to about 3.7, and most researchers put it at a little bit older than that. Okay, so at that point in time, about 4 billion years ago, we had hydrothermal processes forming things like sulfide minerals. We had weathering forming things like clays. We had, precipitation processes forming things like borates. But we actually needed a bit more mineral evolution in order to get life. And we needed a certain level of mineral evolution in order to get life. Okay, because as it turns out, one of the things that is really good at catalyzing the reactions of different molecules and forming new molecules is mineral surfaces. And experiments have shown that over and over again. We can take, for example, hydrogen and nitrogen gas, okay, that's just floating around in the air. And when you heat it up a little bit and expose it to a mineral surface, the mineral surface catalyzes the formation of ammonia and you get a new molecule. And the same thing happens when we use organic molecules. And we've actually discovered another interesting aspect that of how organic molecules interact with mineral surfaces is that all of the molecules, or at least most of the organic molecules that life uses, okay, most of the organic molecules in your body have a handedness. And what we mean by that is that the left-handed version of the molecule is different, okay? It's geometrically different than the right-hand version of the same molecule, okay, with all the same atoms and all the same bonds. But the molecules in your body tend to use only the left-handed versions of those molecules. How could life have done that? How could life have only used the left-handed versions? Well, one of the ways that it could do it is by interacting with mineral surfaces, because mineral surfaces are also handed. They also have left-handed versus right-handed configurations, okay? And there are surfaces on such minerals as quartz and calcite that have handedness. They are either left-handed or right-handed. And that's one of the really interesting things about the chemistry of minerals. In fact, every quartz crystal that you've ever had, that you've ever held in your hand, is either right-handed or left-handed. And there's a way to tell. You can do diffraction and tell whether it's left-handed or right-handed. But without that, you would not be able to tell. So now I'm going to give everybody sleepless nights, right? You're going to wonder if that beautiful crystal of quartz that's in your collection, sitting on your desk or whatever, is it left-handed or right-handed? You don't know. But the bottom line is that many minerals have surfaces that are handed like this. Calcite is one of them. And so the left-handed version of a molecule can react on that mineral surface better than, say, the right-handed version of that same molecule. So mineral surfaces also provide a good way to explain why so many of the biological molecules that we see in the natural world are left-handed. Okay, so some mineral surface at some point, in time, maybe back 4 billion years ago, selected the left-handed version of these amino acid molecules, and now that's why we have left-handed amino acids in our bodies. Okay, so for a long time, since life started, from about 4 billion years ago when life first started, up through around 2.5 billion years ago, life was around. But the atmosphere and the environment on Earth was very different because we didn't have oxygen. There was no oxygen in the atmosphere. Okay, and that limited the diversity of mineral species that we could have had, because many minerals need oxygen in order to form. Okay, so that's actually why we only had these 1,500 mineral species at that point in time. Okay, we had things like oxides and carbonates and sulfates. Okay, we had all of those things, but the number of species was not that large. The number of species wasn't nearly as large as it could potentially be. Okay, so we have things like the carbonates that are formed in these stromatolites that you see on the right image. We had some limited number of iron minerals like you see in the left-hand image there. Now, what changed? The thing that changed is that life evolved these critters called chemolithoautotrophs. And that's a mouthful. And of course, I'm not a biologist, so I'm not by any means an expert on how these organisms work. But essentially, chemolithoautotroph means chemical rock by itself utilizer is the rough translation. So in other words, these microbes are able to perform their own metabolic process to make their own food. Okay, they make food out of just materials that they find in abundance in their surrounding environments. And we call them, traditionally they have been called cyanobacteria, but in reality, they're not actual bacteria in the way that we use the term today. They're actually belong to this group called Archaea. And here are some images of them. There's a whole bunch of different varieties of them today, of course, but in the Earth's past, they were new. About 2.5 billion years ago, they came into play and they figured out how to do something incredible. They figured out how to take carbon dioxide from the atmosphere, straight out of the air, and combine it with sunlight and combine it with water, and they used it to make their own sugars. And those sugars were their food. And the byproduct of this process was oxygen. Okay, so you can probably tell what process I'm talking about. This is photosynthesis, or specifically oxygenic photosynthesis. And we estimate that this happened sometime between 2.5 and 1.8 billion years ago. Okay, and once we had that happen, that brought us up to about 4,500 mineral species. So in other words, we suddenly, in a relatively short window of geologic time, we suddenly developed about 3,000 new mineral species, simply because the cyanobacteria figured out how to do photosynthesis and they started putting oxygen into the atmosphere for the very first time. Okay, so that oxygen began to accumulate. And because of what living things did, because of that photosynthesis, it generated all these new minerals, and we estimate that approximately 2/3 of all of the known mineral species today would not have been able to form in an anoxic environment. And therefore, all those new species, all these new minerals are a direct consequence of biological activity. Okay, so that means that minerals impacted life and life impacted minerals. Okay, now if we look at what oxygen was doing throughout Earth's history, because that's a major part of the story, it started at very, very, very low, vanishingly low levels. And notice that this is a logarithmic graph. Okay, so down here we've only got 0.0001% of oxygen in the atmosphere. Okay, it stayed that way, okay, practically no oxygen at all for a solid 1.5 billion years. The first 1.5 billion years of Earth's history were practically without oxygen. But then remember, around 2.5 billion years ago, we had those cyanobacteria begin this process of photosynthesis and started pumping small amounts of oxygen into the atmosphere. So on our logarithmic graph, that took us up quite a bit to this level. Okay, well then for a while, nothing happened. But about 600 million years ago or so, we experienced another rise in oxygen, okay, that was also connected to life. Okay, so there we don't, early in Earth's history, we don't have a good record, okay, it's a little bit spotty, but from what we can gather is very low levels. Okay, but when the amount of atmospheric oxygen rose to about 1% or so, it gave us huge deposits of new minerals. So for example, one of the major things that changed was iron chemistry. Okay, iron mineralogy diversified a lot because iron in the early Earth was normally just in the +2 oxidation state. So in other words, its atoms had a total charge of +2. But once I pumped more oxygen into the atmosphere, that grabbed electrons away from oxygen and reacted it to Fe3+. Okay, so now it's in a higher charge, it's in a new oxidation state. Now, since Fe2+ is soluble, okay, so in the early oceans, there was lots of iron just floating around dissolved, just like salt is today. But when that rise in oxygen happened, it started filtering in the oceans and it changed that soluble Fe2+ to insoluble Fe3+. And so all of a sudden, a bunch of iron oxide minerals started dumping out of the ocean. They all precipitated. We formed lots and lots of magnetite and hematite. And that's, of course, is exactly where we get banded iron formations. Okay, that's what these are. Here in Western Australia, there's several places where you can see really extensive deposits of these banded iron formations. So all of a sudden, lots and lots of iron oxide formed. That was one of the key events that took place in mineral evolution. Okay, so we made these banded iron formations. Okay, they're around 2.7 to 2.5 billion years ago, as oxygen in the atmosphere was starting to ramp up because cyanobacteria were just starting to do their thing. Here's some other photos from a national park in Australia, and you can see the extent of these things. Okay, they're in some cases kilometers thick. So this was a huge event in mineral formation in Earth's history. Now, I wanted to know, myself and the other researchers that I was working with, we wanted to know, can we look in detail at other events in Earth's history and can we see these sorts of changes? So these banded iron formations, for example, we know resulted from the chemical change of iron +2 to iron +3, okay, changing its oxidation state. And I wanted to know, could we do this with other elements, with other groups of minerals as well, and look in more detail at the changes that were going on as our atmosphere built oxygen up into it. So what I did was I looked at the diversity of manganese minerals. So manganese is another element in the middle of the periodic table that can also change its oxidation state. So in other words, it changes its charge, its positive charge, according to its environmental conditions. So for example, on this graph here on the y-axis, I'm plotting, it says log FO2. FO2 is the oxygen fugacity. So here we're just talking really about the amount of ambient oxygen in the surrounding environment. And on this axis is pH. That's less important for what we're talking about. But notice that in this diagram, it shows different species of manganese that are stable. So over here, I have Mn2+ in solution that would be stable. Along here, I've got 3 different manganese oxide minerals that are stable, okay, where manganese has different charges in each mineral. So for example, down here at really, really low oxygen levels, I have this mineral, santaroite, that would be stable, and it has manganese in the +2 and +3 state. At little bit larger oxygen levels, I can get more manganese in the +3 state. Okay, so there's, for example, purpurite, it's manganese phosphate, and it has manganese in the +3 oxidation state. And then at higher oxygen levels, finally, I can oxidize manganese all the way to +4, and I get manganese in the +4 oxidation state. So for example, in ramsdolite and pyrolusite, in quite a few of the common manganese minerals that we see today. So how did this change over Earth's history? Did we get different groupings, different chemistries of manganese minerals at different points in Earth's history? So I assembled all of the data that we had from our database, put it all together. It took a long time, but we wound up with a database showing when different manganese minerals occurred in Earth's history. So here is the histogram, okay? So this is kind of similar to the zircon histogram. I'm showing you the ages of all the different manganese minerals that formed at all the different stages in Earth's history. And here they are, and you can see once again that we get some spikes in activity during the periods of these supercontinents, Kennerland, Columbia, Rodinia. Rodinia seems to be a little bit different for some reason. There's a spike at the very beginning and a spike at the very end of Rodinia. We're still working on exactly why that is, but the overall trend is very much the same. We form new mineralization events with the formation of the supercontinents. But in particular, notice that back in deep time, okay, 2.5 billion years and older, most of these spikes, these big spikes, are red colored to mean Mn+2. So in other words, the most reduced, the lowest charge of manganese. And as we proceed, we get more and more occurrences of the yellow and purple, which are the +3 and +4 manganese minerals. Okay, so we see the supercontinent trend on there, and we also see this trend in oxidation state. So what I did was I took all of the occurrences and I plotted up the average oxidation state of manganese versus age. Now, as it turns out, we didn't have a lot of old data. Okay, so once you get past 1 billion years or so, we didn't have very much data. But here I'm showing you the data going back to 1,000 million years ago. So in other words, 1 billion years ago. Started getting better data there. And here you can see that the average oxidation state of manganese starts out at a low level. And there's a little bit of a gap right there. And then we pick it up again. And it starts to change over time. It goes through a maximum, goes down, goes up again, and then it levels out. Now, how does this compare to what oxygen was doing in the atmosphere? Well, we have some independent measures of that. Okay, if you follow geochronology and the work that's done on Earth's early atmosphere, then you know there have been various reconstructions from various different lines of evidence showing what the atmospheric oxygen level was at different points in Earth's history. So for example, Berner and Canfield did one study. Okay, so Don Canfield is one of the major people involved. Heinrich Holland also did lots of reconstruction. So here are some of their reconstructions shown in red, green, and blue. Their reconstructions are plotted right here. And my data for the oxidation state of manganese is shown in these black data points, just like I showed on the previous slide. Notice it follows essentially the same trend, except that the peaks don't happen at the same time. Okay, and this is something actually that we are publishing right now. This is getting published. It's in press right now with Nature Communications, and will come out very soon. So what do we see? Well, the oxygen levels also went through a little bit of a decline, went through a maximum, went down, and then came up and leveled out again. And if we simply shift those over, if we time shift them over on the x-axis by 66 million years, now you can see they line up really well. Okay, that trend of decreasing oxygen, then increase, decrease, and then leveling out again is very much followed by that manganese data, showing that the different manganese minerals were changing their average oxidation state. We're getting different groups of manganese minerals as we go through that last 600 million years of Earth's history. And it was changing as a direct result of that change in oxygen level. Okay, and you can tell that was the direction of causality, because the time shift, we had to time shift the atmospheric oxygen in the forward direction. Okay, so we shift those oxygen values forward, and all of a sudden they show the same trend as manganese oxidation. So what we can conclude from this is that there were different sets of manganese minerals that were forming at different times depending on how much oxygen was in the atmosphere, and specifically how much oxygen life was adding to the oxygen to the atmosphere, because that was what was driving many of these atmospheric oxygen changes. Okay, so this was a really fascinating thing that we found. And by the way, we believe that we can do this with many other sets of mineral data as well. Okay, so that pretty much wraps up the talk. There's a lot more that we can do with this data, but just to sort of bring what I've talked about to some conclusions, we know that the Earth has transformed repeatedly and has evolved continuously over its 4.5 billion year history. We know that the mineral content of the Earth has changed many times. We know that we have accumulated new minerals over time, and the way in which that's happened can tell us an awful lot about not only the story of the solid Earth, but also about life, because we know that minerals and life have co-evolved over time through numerous different chemical, physical, and biological processes that were all intertwined with each other and were affecting each other at different stages in Earth's history. And we know that now that we have these large mineral data sets, we can use them, we can leverage all of this data and statistically look at the trends of how many minerals there used to be at points in the Earth's past, how many there are now, how they've changed over time, and how they all record the story of the Earth. And I think that that is all I have. So I will, I don't think I saw anybody asking any questions, but I'll end it right there, and we can take some questions. I can leave the slides up as well.
Could you go over the 66 million year offset in the manganese and oxygen? Because there's not, if there's that much offset, what's the causal connection?
Yeah, that's something that we've been working on. Yeah, thanks for that question, because this is a super important thing. You know, what is it, by what mechanism is the oxygen that's accumulating in the atmosphere actually getting into the Earth's crust and transforming the chemistry of manganese minerals? Yeah, that's a really crucial thing that we need to answer. We don't know exactly, but we have a guess. Because with this 66 million year time lag, essentially, that it takes for oxygen to infiltrate the crust and to equilibrate all those manganese minerals, that long of a time lag, we're not just simply talking about fluids filtering into the very uppermost portion of the crust. We're talking about something much longer term than that, because fluids, we know, can migrate on a scales of years or hundreds of years. So what we think is going on is that these are very broad tectonic processes that are at work. We think that with subduction, atmospheric oxygen is going to dissolve into the ocean. That's going to raise the oceanic oxygen fugacity. That is going to filter into oceanic crust and raise the oxygen fugacity of the oceanic crust. And that is going to subduct. It's going to mix with upper mantle material. It's going to mix with material in the lower crust as things melt and come back up. So we think we need this very broad scale tectonic recycling of crustal material in order to oxidize the crust to the point that we get these changes in manganese minerals. So that's kind of our operating hypothesis at the moment, but it's an excellent question. And we need more data. We need more studies like this in order to delineate that. Does this happen with other minerals that form in different kinds of environments? Do we see a similar sort of time shift, or is it a smaller time shift? We need that data. We need those studies in order to figure out what kinds of mechanisms specifically would be involved.
Actually, as soon as you started to talk, my thought was that somehow maybe subduction has something to do with this, but there ought to be other people out there who have figured out what the cycle time is for ocean floor to get subducted and be reprocessed at depth and come back to the surface. Just thoughts. Thank you very much.
Yeah.
This was great.
Yeah,
I started out collecting rocks when I was in minerals when I was 9 years old, and I'm almost 75. So this I learned more about mineralogy tonight. I think I learned more about mineralogy tonight than I have in a whole lifetime. So thanks.
Oh, wow. Well, thank you. Thank you so much. Yeah, I think you're exactly right. I think subduction does have a lot to do with it. And we actually are now just starting to learn about the timing of some of these processes. I know people out in California, like at Berkeley and Cal State, and people at the Smithsonian in Washington, DC, who are looking at this exact issue and are trying to look at the timing of how subducted material changes the oxidation state, for example, of the upper mantle. And how fast does that mixing take place? What role do magmas and fluids play in dispersing that material and changing oxidation states? So we're just now starting to get a handle on some of those things. So yeah, one thing I'd like to do is collaborate with some of the people who are doing that work and figuring out, does the timing and does the sequence of events make sense with the data that we're getting, for example, on the manganese data sets.
Hi, Dan.
Questions.
This is Suzanne Mills with the Carnegie Museum of Natural History and Invertebrate Paleontology section, and I really have enjoyed your talk. And I put a question in the chat, but I'm not sure if anyone's moderating the chat, so I thought I'd just pose my question.
Oh, okay.
I work with a big data set, and so I'm very interested in understanding more about your big data set and exactly how who is it who's entering the data, and how confident are you that your data set represents the full diversity of minerals and localities of these minerals on Earth?
Yeah, that's a great question. One of the terrible conundrums about doing this sort of work is that in order to get good statistical results, you need lots and lots of data. You have to have a huge data set in order, to pull off these kinds of analyses. But the flip side of that is that if you're trying to get as much data in as quickly as you can, how much quality control can you do? How sure can you be that these are robust geologic ages, that there's, and that this is representative of the mineral deposits that we find all over the world? So those are great questions. Those are things that we've been trying to address. The way that it's done is, in particular, the rough database of all the mineral occurrences. We use the IMA mineral list for all of our mineral species and for the basic mineral data. And we get our numbers of mineral localities comes from the database at MINDAT that is maintained by Julian Ralph in the UK. And so we've actually collaborated with him to make sure, okay, we want to define, for one thing, we want to define a locality consistently, as like one geologic formation that has a particular geologic age, for example, because you can look at localities at many different scales and many different rocks that are related to each other. So that's one thing, is how do you define locality and and keep a consistent definition of that for purposes of your count. Also, how do you make sure that the ages are accurate? Where do the ages come from? Well, in our database, we have them coded. We have them coded by, okay, this one was actually done with a radiometric method on the actual mineral that we're talking about. Then we have a whole other set of them that are done with a co-occurring mineral. Okay, then there's another set of them that are done, for example, just through relative age dating brackets. We've got a whole system worked out for this, and all of the geologic ages are coded as according to exactly where they come from. And in these studies, we try to use just the most robust set of ages if we can get away with it. If not, then we throw in the next category and we look to see, how much does that change the result. So that's a little bit about how this is done. The data set is worked on and is added to mainly by researchers at the University of Arizona who have been working in Bob Downs's group. He's got entire teams, of grad students and so forth that work on going through the literature and using a consistent method to pull out this data and add it to the database. But it's definitely a lot of work. It takes many years to build a database large enough to do these kinds of studies. But they're still working on it. They're still adding to the database. We're still grappling with some of these issues as to, for example, how we define a locality. So those are all important issues. And, other people who are working with big databases, we would love to talk to you. We would love to figure out, how are you doing things? What tricks have you learned? We can tell you how we're doing things, and we would love to communicate about, a consistent way to do this and how we can build even bigger and better databases. Sorry, I talked for a little while there, but that's a really
no worries,
crucial
Dan.
issue.
So I could go through we have some questions in the chat, and I can go through some of these, for you.
Okay.
So Kent had put in, could the events of mineral formation be related to energy changes? Like, I guess I don't know if you answered that with your subduction question.
Could they be related to what?
Energy changes.
To energy changes. So meaning like maybe just the amount of energy in the environment, like heat energy and things like that.
Possibly. Kent, if you want to come elaborate.
Yeah, feel free to jump in.
Oh, I'm just wondering if it's cosmological or any other kinds of energy. Again,
Okay.
Heat, things like that.
Yeah, I think heat is playing a crucial role, and in particular, I think temperature and pressure regimes in different parts of the earth are playing a really big role, because I heard you in your introduction, I heard you emphasize phases. So I gather that many people here look at phase stabilities at different conditions, and of course you can plot up your PT phase diagram of what chemical components forming different mineral phases at different PT conditions. I think that's playing a really major role here. I think that when you have tectonics going on, you have subduction, you have collisions that are generating new pressure, temperature environments, then you're moving different portions of the earth to different parts of that PT phase diagram, and therefore you're producing different minerals. So certainly chemical differentiation has something to do with it, but also generating these new pressure temperature combinations, new pressure temperature and EH and pH environments is going to change what minerals will be stable, and that's going to form whole new mineral deposits different from what you had previously. So these new mineralization events that are expanding mineral diversity, like when we have the supercontinents, I think that's a big part of what's going on.
Wonderful. Amy wants to know if you've ever had a mineral named after you.
Oh, no, I have not had a mineral named after me. I would love that, but sadly, if you look at the list of IMA approved mineral species, you will find hummerite. There's already a hummerite, and it's a beautiful orange vanadate mineral that comes from a mine in Colorado, the Hummer mine. So apparently there was already a guy named Hummer, and he had a mine named after him, and then the mineral was named after the locality, as often happens. So there's already a hummerite, but you never know. Somebody could find a new mineral and name it Dan Hummerite. I would be okay with that. For example, there's Jim Thompsonite.
Oh,
It was named after Jim Thompson.
It's possible you can dream.
That's right. I can dream. I have a lot of colleagues, and sometimes we discover new minerals. So yeah, we'll see what we can get.
Phil says, great presentation. Thank you for presenting. Your database must be huge. What kind of database is it? And what level of effort is required to maintain it, and house it?
Okay, yeah. So I guess I touched on that a little bit with somebody else's question, but I will let me move backwards through my slides, and I can show you. And I actually encourage you to go to that rough website, and you can explore the database yourself. There's actually a lot that you can do with it. Okay, I have to rewind even further here. Here we go. Here's the database. Yeah, so the database is on an open web platform that is maintained at the University of Arizona, as I mentioned, by our colleague Bob Downs. And he's done a huge amount of the work in maintaining this database. So we have the list of mineral species here, some basic data about it, the mineral group that it goes with, its chemical formula and so forth is listed in the database. And then we have this chemistry filter where you're able to filter it by chemical makeup. And then we've got, and up here are buttons where you can look up the mineral on Google. You can look it up on the Handbook of Mineralogy, which is that HOM. You can look it up on the American Crystal Structure Database, which is that button right there. So all of those links are sort of coming out of the database. So yes, it's a large database. It's got the nearly 6,000 of the mineral species that we now know. It has, I think, something like 1.5 million data pairs of minerals at a location. So in other words, calcite at the Homestake mine, gold at the Homestake mine, orthoclase at Mount Rushmore, there are 1.5 million of those, of data pairs of a particular mineral occurring at a particular location. So yes, so it gets to be, especially when you throw in the locations and the geologic ages, it gets to be a very, very large database. And it takes a good server. They've got a computer cluster there that maintains this database. And it's quite a hefty thing, but it's wonderful that they've made this web platform, and you can go to this very website, and you can play around with the database as well.
Oh my, we are running up on kind of like 10 minutes of questions left. So we only got a couple more questions we can do because I don't want to take up everyone's time there. One of the questions out there is, are there any underlying assumptions for your statistical model to predict the number of minerals that, quote unquote, should exist, the ones that would be present on Earth? What about minerals that can't be observed, like those that formed at high temperature or pressure?
Okay, yeah, great question. So for one thing, yes, it is based on the assumption that we continue discovering minerals in the same ways that we have been. So for example, nowadays we are, in the past, we used to discover minerals more slowly. And a big part of the reason for that is that many, many minerals form only these tiny little nanophase crystals that you can only see with an electron microscope. Well, obviously, before we had an electron microscope, we didn't know about any of those minerals. Okay, we were discovering minerals much more slowly. Well, once electron microprobes and microscopes became more prominent, starting in the 1950s, all of a sudden our pace of mineral discovery started to increase, and we started kind of expanding that pool. And if you look at those, in fact, I can go to one of those accumulation graphs. There we go. If we go to one of those accumulation graphs, our rate of mineral discovery increased. And of course, our statistical extrapolation depends on that rate of increase. So if we change the way that we do things, or we discover a new technology that allows us to find minerals in a new way, that definitely influences the predicted number of species that we would be able to find. Okay, so as our method of mineral discovery and our definition of what a mineral is changes and expands, the number of things that we expect to find also expands. So that's one component of it. I forget, was there a second component
we
to the
can
question?
we can keep going. So just two more questions.
Okay.
So given the data, would it be possible to suggest timeframes for mineral formation and then translate that into mining targets?
Yeah. And actually, once we really started playing around with these databases, we developed some collaborations with the USGS. And we went out to Virginia, where the USGS is headquartered, and we had an entire meeting about, how can we use all of this data to predict where other good ore deposits are going to be. Because these trends of minerals occurring at specific geologic times, certain minerals being associated with each other, we said, hey, that means if we look at the statistical trends, for example, gold, look at what geologic times was gold forming, and what geologic environments was it forming in, what minerals is it commonly associated with. And you can look at the common trends there, and you can start predicting, oh, well, in these other environments, we would predict to find gold as well. So so some of our database we have actually given to the USGS, and they're using it to develop techniques like this right now.
Then our last question, I think, is a good one. So perhaps this evolutionary approach to Earth's mineralogy will have applicability to characterizing and understanding the evolutionary history of neighboring planets like Mars.
Yes, that's another thing that these are fantastic questions. These are actually all exactly the things that we've been thinking about. So we're very early in that stage of thinking about other planets, but one idea that we have is that if you plot the ways that minerals co-occur with each other, if you kind of draw lines, draw connections between them, you can develop entire network diagrams. And I know, Mike, I think you've seen quite a few of these network diagrams.
Oh my, have I seen so
you were
many
at Carnegie, and you were even working on network diagrams for fossils. Yeah, so you can form these intricate networks and look at the ways that mineral species co-occur. Well, the species that we have and the ways, the patterns in which they co-occur is very strongly a signature of how they arise and how they form. And as I talked some about in my presentation today, many of the mineral species that we have on Earth, they're hydrous, they're oxidized, okay, they're not like things that we find on other planets. Those entire sets and networks of oxidized and hydrated mineral species, we think are very much a biosignature. If they only occur when you have life, then that's a biosignature. So you can look for those same kinds of minerals on other planetary bodies, look for them spectroscopically, and perhaps use those mineral groups as a biosignature and be able to figure out what the environment was like and whether there's life on other planets. So those are some of the things that we're thinking about doing as well. But of course, one part of it is that we've actually got to find a significant number of these other minerals on other planets before we can really take a close statistical look at them. So, we need more exploration. We need more, spectroscopic studies of planets if possible. So, we need our cosmochemists and our astronomers and astrophysicists to get involved as well.
Wonderful. All right. Man, is my video actually on? I can never tell sometimes. That was a great talk. We had a lot of good, I think we had some really great questions on there.
We did. Well. I don't even think we got through all of them. I'd love to keep answering questions, but
I know we could be here for way too late. We wanted to really thank you for speaking, and I'll let Kent finish it up.
Here, I'll stop my screen share.
Yeah. Daniel, thanks for speaking to us. That's, I think one of my first comments I wrote down is you changed my perspective. Even the idea of the minerals versus the words in a book is an interesting perspective. I did check in on your rough, what is the rough info IMA website, and it's boggling, the number of even just the minerals that start with the letter A. There's hundreds.
Yeah,
Appreciate your time to talk with us, and again, changing our perspective, adding to the few more grooves in my brain. And
well, thanks so much. And thanks everybody for joining me, and thanks for all the great questions. If you have any further questions, I'm happy to talk to people. My email is just daniel.hummer@siu.edu. So you can find me that way and send me a message.
great, thank you very much. Have a good evening.
Thanks, you too.
All right, thank you, everyone. I'm going to end the meeting. Have a good night.
All right, thanks, Mike.
All
Good
right,
to see you.
goodbye, everybody.